This is 2.4, the average rate of change of a function. And this concept may look a little familiar, but just keep in mind that this actually leads to a bigger concept as we go throughout the year. So the average rate of change, here's a chart or a graph that notice it's starting at 6 a.m. It says it down at the bottom, starting at 6 a.m. And this is based on hours and miles, note in 10. So this would be 10 miles, 20, 30, 40, and so forth. And I want to know the average speed between 6 a.m. and 6 p.m. Well, average is just like the distance traveled over the time. So if you look between 6 a.m. to 6 p.m., so basically we have a 12-hour time frame, and it starts at 6 a.m. So we're going from 0 to 12 is really what it looks like. And then notice it travels 84 miles. Again, here's 10 miles, 20 miles, 30, 84. So it stops at 84 miles. And then notice how long it's taking them to actually 1 hour, 2 hour, 3 hours. So it's a 12-hour time frame. So 84 divided by 12 would be 7 miles per hour. And again, if you notice, if you actually go 7, this is actually the slope of the line, okay? So this is 7 over 1. So just if you had to, remember this is 10. So if you had to go up 7 and then over 1, see it's right there. Up 7 over 1, up 7 over 1. And so that's the average rate of change between those 2 points. And again, some things, you can actually do any 2 points that you want. I could have asked you from here to here, the average rate of change between there and there, or the average rate of change from here to there. So I'm asking you basically from the beginning to the end is the average rate of change. But I could ask you more specific between hours 6 and 8, or between 10 and 12, or So I'm asking for the average rate between the entire time period. Much like if we ask for like the average grade change or the temperature change, or over a 1 hour or a 5-hour difference, it makes a huge difference. So in this particular case, I'm asking for the entire 12-hour period. All right, so here's a definition that you need to be familiar with. So the average rate of change is basically the change in the y over the change in x. So if based on if you have your graph y and your x, so the change in y over the change in x, you should have seen this symbol before. It's like a triangle, and that means the change. So the change in y over the change in x. Now this is the way that you need to be familiar with it. A lot of you guys might think of this as like y2 minus y1 over x2 minus x1. You might be used to something like that. But notice you have the point. Normally we have x, y, x, y. So this is the point A, and then f of A. So when you plug A into the function f, that's called f of A. So when you plug B into this function, that would be called f of B. So basically you're taking f of B, y2, minus f of A, that's y1, and then over B minus A, so this would be x2, x1. So it's really the same formula that you're used to. It's really finding the slope of the secant line. Remember what a secant line is, just like what we did earlier, and here's a graph as well. It's basically a secant line is connecting 2 points from anywhere on the function. Any 2 points connected is a secant line. So we're basically finding the slope of that line. And it's usually, we're going to be using this formula right here. And again, it's this same familiarity that you need to be used to. All right, so let's look at an example. Let's look at several examples. So here's a function, f of x equals x minus 3. You could graph this if you want. We could look at it and see what it looks like. So just drawing a quick graph, and this is not accurate. It's not on graph paper. But this is basically what it would look like. And so if we wanted to find x equals, the net change between x equals 1 and x equals 3, notice what we're going to be doing. We're going to find f of 3 first, and then minus f of 1. That's really what we're doing. We're substituting x, 1 in, and then x3. We're going to substitute those in. Again, just recall back to the formula, f of b minus f of a. So we're going to take the net change between those, and then we're going to end up literally taking the change in dy, so 3 minus 1. So f of 3, again, you can look at the graph if you want. So, at 3, when x is 3, where is the graph at? And it's at 0. But you can just plug that in, 3 minus 3. And so you're going to get 0. So 3, 0 would be the first. And so the same thing when I plug in if x is 3, or x is 1, if I plug in x is 1, again, you could look at the graph. When x is 1, where is the graph at? Or you can just simply plug it in here. So 1 minus 3, and then squared, and that's going to give us 4. So notice the average rate of change, and again, we're talking about if you look at it as from a picture standpoint, I want to know from this point to this point, the secant line between that, what is basically the slope of that line, and it's -2. And you can see that it is going down. This is a -2 slope, -2/1 slope of that secant line. All right, so the same thing for the next point, the next average rate of change. So here we have x equals 4, x equals 7, so we're going to do f of 7, and then minus f of 4, and that's over 7 minus 4. So we're going to substitute those in, and notice I ended up getting 5 as the net change between those. And again, you can always check it, like if you look at the picture of the graph. I'm looking for when x is 4. So when x is 4, you can see where it's at. It's at 1 right here, and then you can see where when x is 7, so it would be off my graph, but it would be pretty high up. It would be at 16, and you can then draw the secant line between that, and the slope is going up 5/1, up 5/1. So you can see the slope between those if you look at the graph. All right, again, so here's the average speed of a falling object using this function. And again, we could graph it if we wanted to. I just really want to know what's the average speed of the falling object between 1 second and 5 seconds. And yes, that's a 5. All right, so if I wanted to find the average rate between those, again, we're using the d of 5 minus d of 1. Again, the function is called d on this particular problem. And then we're going to take 5 minus 1. And so we're just going to substitute those in, and then evaluate the function to be able to do that. So I evaluated d of 5, just substituted 5 into that. I got 400. I substituted 1 into the d function and got 16. Subtracted, divided by 4. So the object is falling at 96 feet per second. Again, you drop an object off of a cliff. You can graph this if you want, and then look at the point. 5. It would literally be 5, 400, and then it would be 1, 16. Those are the 2 points, and then you can literally calculate the slope between those 2 points. All right, and let's look at another example. So here's a time and a temperature chart that you can see, and I want to find the average rate of the temperature change. And if you notice on this, it starts at 8 a.m. and the temperature was 38 degrees Fahrenheit, and then 9, 10, 11, 12, 1 p.m., 2 p.m., 3, 4, 5, and you can see the temperature change between each of those. So between 8 and 9, again, you're going to do f of 9 minus f of 8 over 9 minus 8. So you just look at the chart. At f of 9, it was 40 degrees. F of 8, it was 38 degrees. And then 9 minus 8 is 1. And so there was a 2-degree average rate of temperature change between 8 and 9 p.m. And between 1 and 3 p.m. So f of 3 minus f of 1 over 3 minus 1. So f of 3, if you look at the chart, was 67. F of 1 is 62. 3 minus 1 is 2. So you can see the average change is 2.5 or 2.5 degrees per hour. That's the average rate. And you guys know in real life, it may drop 5 degrees in 1 hour and only 1 degree the next hour, but the average rate of change. So that's what we're looking at. And then finally, just something that you need to be aware of, just as a reminder, you already know this, but linear functions that makes a line, and usually y equals mx plus b is the typical line that we're going to be using, have constant average rate of change. Remember, the average rate of change, another word, is slope. Okay, so y equals mx plus b, and we can literally see the slope right there is 3. So it doesn't make a difference what we calculate, we're going to end up with 3. And just to prove the point, as far as showing work, we're going to do f of 2 minus f of 0. 2 minus 0. And so f of 2, if we plug this in, it would give us 1. F of 0 would give us negative 5. And then over 2. So notice this is a negative 5 because when we plug 0 in, 0 times 3 is 0. 0 minus 5 is negative 5. So 1 minus a negative 5. So this will give us 6 over 2, which is going to give us 3. But again, we knew the slope already was 3. Well, the same thing here, f of 5 minus f of 1 over 5 minus 1. And we're going to end up getting 3 as the same result. So just as a reminder, if I give you a linear function, then the average rate of change is always constant.